Hi, I'm Tom Deshiell, Director of R&D at Matrix Shafts. And today we're going to answer some more questions from the feedback we received on the Hacker's Paradise Shaft Tech series. So we had a lot of people ask what the difference was between bend point, flex point, balance point, and tip deflection. So they're all slightly different and some are not related at all, so we're going to go over them all in this one video. We're going to start with kick point, which is pretty much used interchangeably with flex and bend point. And what people are trying to describe when they say that is where the maximum bending occurs in a shaft. We've got three shown here. We've got a high kick point, mid kick point, low kick point. And you see how the curvature changes down the shaft. And this changes the launch angle of the ball. High kick point gives you a low launch. Low kick point, there's more deflection down here, get a higher launch. Now, in reality, it looks like this kick point moves quite a bit up and down the shaft, where in reality, it really happens down here in the bottom third of the shaft in the tip region. Now, people will describe this or measure this several different ways. All depends on the equipment they have. I've seen it done at least these three methods I have shown up here. One is buckling the shaft axially, putting a load on both ends. The shaft will deform. You find the area where the biggest deflection occurs, and that defines your kick point. Another way to do it is to use a cantilever method where you clamp the butt end, weight on the tip, you draw a line from the tip to the butt, and you find the maximum deflection at that point. Again, you can locate your kick point. The other way to describe something as a high, mid, or low kick point is just to use a ratio of measurement values of butt flex to tip flex. And as that ratio changes, they will use it to describe a high, mid, and low kick point. And this diagram down here shows a tip or butt deflection setup. You have your shaft in here, clamped on one end. You have a mass to deflect the shaft. And then from the opposite end of the shaft, you can measure your deflection from the horizontal. A lot of companies will put one or both of these tip and butt deflections to describe their shafts and to distinguish them between family lines. Now, one thing that isn't related to the deflection is balance point. And balance point describes the center of gravity location of the shaft. And it's the point at which the shaft will balance. And this is shown here. And this will have a major influence on club swing weight. When you move the CG down towards the tip, it will increase your club swing weight. If you move the CG towards the grip end, it lowers the club swing weight or allows you to use a heavier head or build a longer club and maintain the same swing weight. And you see that a lot today with the larger, higher MOI heads that are also built to a longer length. Now, to manipulate this position, we have to change where the material is in the shaft. So the thickness of the shaft varies from tip to butt. We've got a close-up here of just the tip section, which is your thickest part of the shaft, and then it tapers down quite rapidly. But by changing what we have in the tip and the rest of the shaft, we can move this CG position. The last question was, how does changing a ply or a flag in a shaft influence the stiffness? So if we go back to our EI calculation here, which when calculated all along the shaft gives us our stiffness profile, we've got our cross section of the shaft and then the material we use. Here's some plies that we would use to make a shaft if we wanted to increase the overall stiffness of this shaft. The easiest way to do it would be just to add more material. But if we wanted to keep the weight the same, we would take this full length ply here and change it from a standard modulus material to a higher modulus material. And then when you replaced it here in the shaft, what you would end up with is a stiffness profile that increases all the way along the length of the shaft. Now, if we wanted just to adjust the stiffness in the tip region, which is the big influence on kick point, we would change the size of that tip flag. So if we made that flag longer and put it in the layup, it's not changing anything in the upper part of the shaft, so the EI profile would stay the same. And then where this flag started, you would see an increase in tip stiffness. So we would do something like that if we wanted to manipulate the kick point of a shaft.